Welcome back to the deep dive. Okay, so today we're tackling something absolutely fundamental. Work, energy, and power. The real bedrock stuff.
That's right. We've got a great set of materials here, instructional summaries, bits from textbooks, all focused on these core physics concepts.
And our goal, really, is to pull out the essentials. What are the key formulas? How does energy actually change form?
And crucially, how do these basic ideas connect to everything? From lifting something simple like a sandbag,
Right.
all the way up to modern energy tech, renewable power, the whole global picture.
You should leave this knowing how change, well, mechanically happens.
Exactly.
And we should give a quick shout out here. The structure for this deep dive, a lot of it came from summaries put together by physics teacher Hakivelli Torun. Really clear, helpful stuff.
Yeah, absolutely. It laid things out very logically. Because look, these concepts, work, energy, power, they're like the language physics uses to describe change. It helps us grasp not just how things move, but why it matters for technology, for the universe, everything.
Okay, so let's dive in. Starting with work. And the physics definition, well, it's stricter than how we might use the word every day, isn't it?
Oh, definitely. That's the first hurdle. In physics, work we use dollars for, it only happens when a force causes something to move. And importantly, move in the direction the force is pushing or pulling.
Right. The formula is simple enough. $1 equals F times D dollar. Force times distance.
But the implication is huge. No distance moved. Then no work is done. No matter how much effort you feel like you're putting in.
Which brings us to that classic example, the one you always see in textbooks, pushing against a solid brick wall.
Right, you can push with all your might, get exhausted, sweat buckets.
Feel like you've done a ton of work.
But if that wall doesn't budge, the work done on the wall, in physics terms, is zero. Zip, nada.
You've used energy, sure. Your muscles burn calories, generated heat.
Biological energy, yeah. Chemical energy converted. But external physical work on the wall, nope.
Contrast that with, say, lifting a weight. The sources mention a weightlifter raising a 100 Newton weight that's about 10 kilograms or 22 pounds up 100 meters.
Now that's work. 100 newtons times 100 meters. That's 10,000 joules of work.
And the joule, that's the unit, a Newton meter, named after James Prescott Joule.
Precisely. So work is about the result, the displacement caused by a force.
Okay, so if work is the result, what about power? How does that fit in?
Power is all about time. It's the rate at which you do that work, how fast you get it done.
So the quicker you do the work, the more power is involved.
Exactly. The definition is power equals work done divided by the time taken. So power is what?
Lift the same weight to the same height, but do it twice as fast.
You've generated twice the power. Simple as that.
The source material had a good everyday example. Lifting a heavy shopping bag, say 200 newtons up 3 meters.
Okay, so 200 N times 3 meters is 600 joules of work needed.
Right. Now, if you dash up the stairs and do that in, say, 5 seconds.
600 joules divided by 5 seconds, that's 120 watts of power.
But if you take your time, maybe stroll up in 10 seconds.
600 joules divided by 10 seconds is only 60 watts. Same work, half the power.
And the watt, that's the unit of power. A joule per second.
Yeah, named after James Watt. And it's amazing how this scales. We talk about household appliances in watts, maybe kilowatts, thousands of watts.
Even cars, historically, used horsepower, which translates to what, about 746 watts?
Roughly, yeah. It just shows how that same basic calculation, work over time, applies across the board, from groceries to engines.
Okay, let's shift gears a bit. From doing work to the capacity to do work. Let's talk mechanical energy.
Right. Mechanical energy is kind of the total energy of motion and position in a system. It's basically made up of two main types, potential energy and kinetic energy.
Let's start with potential energy, or PE. This is stored energy, right?
Usually stored due to an object's position or configuration. The most common one we talk about is gravitational potential energy. It depends on height.
The formula being PE equals mghi. Mass times the acceleration due to gravity times height.
The higher you lift something heavy, the more gravitational potential energy you store in it. Think about water behind a dam.
Yeah, that water, way up high, has enormous potential energy just because of its position.
And when you let that water flow down...
But that stored energy gets converted into the energy of motion. Which brings us to...
kinetic energy. But just before we jump there, we should quickly mention elastic potential energy, too.
Oh, right, like in a stretched rubber band or a compressed spring.
Exactly. Stored energy due to deformation. But for large-scale stuff, like power generation, it's usually that NEM pod, the gravitational potential. That's key.
Okay, so now kinetic energy, KE. The energy something has because it's moving.
That's the one. Its formula is 10 E equals 12 V/2. 1/2 times the mass times the velocity squared.
And that squared term, the v/2, that's really important, isn't it?
Oh, it's absolutely critical. This is where the physics really bites. Kinetic energy increases linearly with mass. Double the mass, double the KE, fair enough.
But velocity,
Velocity is squared, so if you double the speed,
you don't just double the kinetic
you
energy.
quadruple it. 2 squared is 4 if you triple the speed.
Wait, 9 times the kinetic energy. 3 squared is 9.
Precisely. And this has massive real-world consequences. Think about cars and safety.
The source material used this example, didn't it? Comparing speeds.
Yeah. A car going at 90 kilometers per hour compared to one going at 30 kilometers per hour, that's 3 times the speed.
So 9 times the kinetic energy.
9 times the energy that needs to be dissipated somehow if you want to stop.
Which means, essentially, 9 times the braking distance under ideal conditions. Or think about the damage in a collision. 9 times the energy involved.
Exactly. Small increases in speed lead to huge increases in energy. That V/2 relationship is unforgiving. It dictates so much about vehicle design, speed limits, safety features.
Is that just a formula? Well, it governs safety margins.
Absolutely. It's why speed is such a critical factor in road safety. Exponentially critical.
Okay, so we have potential energy stored, like height and
Right.
kinetic energy, motion,
Okay.
and they can convert back and forth, right? Like on a roller coaster. PE at the top becomes KE at the bottom.
In an ideal world, yes. On a frictionless roller coaster, the total mechanical energy, PE plus KE, would stay constant. Energy transforms, but the total amount remains the same.
But the real world isn't ideal. And the sources bring up this concept, the energy graveyard. What's that about? If energy is conserved, how can there be a graveyard?
That's the crux of it. We need to distinguish between the law and the reality of usefulness. The law of conservation of energy is absolute. Energy cannot be created or destroyed. Total amount always stays the same. But in any real system, you always have things like friction, air resistance. These forces do work, but it's work that converts that nice, useful mechanical energy, the PE or KE, into something else.
Heat.
Primarily heat. Low-grade thermal energy. It warms up the interacting surfaces, the air.
So the total joules are still there. They haven't vanished.
Correct. The total energy is conserved. But that energy is now dispersed. It's disorganized. You can't easily gather it back up to make the roller coaster go up the next hill or power your car.
It's become unusable, degraded.
Exactly. Degraded is a good word. It's been converted into a form that's essentially useless for performing further mechanical work. Think about braking a car.
All that kinetic energy the car had.
Gets turned into heat in the brake pads, the discs, the tires, the air. The energy is still accounted for, conserved, but it's just radiated away as heat. You can't use that heat to get the car moving again.
So that's the energy graveyard. Energy that's still technically there, but effectively lost for useful purposes.
Right. It represents the inevitable inefficiency in any real-world energy transformation. Some energy always gets lost as waste heat due to friction and other dissipative forces.
Which explains why that roller coaster in reality can't keep going forever. Each time it goes up and down, a little bit of energy is lost to friction and drag, converted to heat.
Meaning the next hill it reaches will be slightly lower. Unless you add more energy, like from a motor pulling it up the initial lift hill, you constantly have to fight that degradation.
It makes sense. It's like an energy tax on every single action.
That's a great way to put it. Thermodynamics collects its tax. Always.
All right, let's look at how we apply these ideas. Simple machines first. Levers, pulleys, ramps.
These are fascinating because they don't create energy and they don't even save you work, fundamentally.
They follow that conservation law, too. Work input equals work output.
Ideally, yes. Ignoring friction for a moment, the work you put into a simple machine is exactly equal to the work you get out of it, or time times out.
So what's the point, then, if they don't save work?
They make the work easier by changing the forces involved. They allow you to trade force for distance, or vice versa.
Like using a ramp and inclined plane to lift something heavy.
Exactly. Pushing a heavy box up a long ramp requires less force than lifting it straight up.
But you have to push it over a much longer distance along the ramp.
Right. You trade decreased force for increased distance. The total work done, force times distance, ends up being the same, neglecting friction. Simple machines are force multipliers, or distance multipliers, but never work multipliers. They just manipulate the trade-off.
Clever. Okay, moving beyond basic mechanics. The source materials also touched on some modern energy solutions. hydrogen fuel cells, for instance.
Yeah, that's about converting chemical energy directly into electrical energy. Hydrogen gas reacts with oxygen.
And the main byproduct is just water, H2O.
That's the big appeal, plus electricity, of course. So potentially a very clean energy source, especially for transport. Zero emissions at the point of use.
Still challenges with producing the hydrogen cleanly and storing it, but the potential is there.
Definitely. And the other one mentioned was geothermal energy.
Right. Tapping into the Earth's own heat. How does that work, basically?
It uses the heat from deep underground. In certain areas, you can drill down and bring up very hot water or steam
And use that steam.
to turn turbines, just like in a conventional power plant. But the heat source isn't burning fuel, it's the Earth itself.
Converting thermal energy into mechanical energy, the turbine spinning, then into electrical energy.
Exactly. It's a great source of continuous baseline power in places where it's accessible, clean, and reliable, using the Earth's stored thermal energy.
Okay, this has been a really comprehensive look, pulling everything together.
Yeah.
Let's try and recap the main takeaways for everyone listening.
Sounds good. I think the first key point is that physics' definition of work. Force has to cause displacement.
Then power. It's the rate of doing work, how fast you do it. PO of AT dollar, measured in watts.
Then mechanical energy, split into potential energy, often female or stored by height, and kinetic energy, 12 milli-VT2 energy of motion.
And that $82 in kinetic energy is huge. Double the speed, 4 times the energy, triple the speed, 9 times the energy. Critical for understanding motion and safety.
Absolutely. And then the big law, conservation of energy. Energy transforms PE to KE, chemical to electrical, kinetic to thermal, but the total amount is always conserved.
But, and this is a crucial credit, real-world processes always involve some energy degradation. Friction, drag, they turn useful energy into unusable dispersed heat. The energy graveyard.
Meaning efficiency is always less than 100%. You always lose some useful energy along the way.
And simple machines. They help us manage forces by trading force for distance, but they don't create energy. Work in equals work out.
And finally, we saw glimpses of modern applications, like fuel cells and geothermal, trying to harness these energy transformations cleanly and efficiently.
It really ties together. And again, thanks to Hakkuveli Torun for the clear summaries that helped frame this. Understanding these rules really is step one to understanding how things work.
It truly is. And maybe, just to leave you with something to think about, we talked a lot about that energy degradation, how usable energy inevitably spreads out, becomes less organized, turns into waste heat. That's a fundamental tendency in the universe driven by thermodynamics.
Towards greater disorder, essentially.
Right. So if all energy transformations naturally move in this direction, towards the state of thermal uniformity, this heat death on a micro or macro scale, what does that inescapable physical reality imply for the really long-term future, for the ultimate limits of technology, of complexity, of civilization itself, if everything inevitably runs down, dissipates? What does that mean for sustainability in the deepest sense?
Wow. That's definitely something to mull over. A connection between basic physics and some very big questions.
Something to think about.
Indeed. Well, that's all the time we have for this deep dive. Until next time, keep exploring the laws that shape our world.